Hello everyone, this is Seven. In today's live session, we'll be seeing the contents of little bit of contents of week 11 as well as week 12. So in the week 11, we would have seen the different types of measures of central tendency, dispersion, skewness, and peakedness, which are measures of central tendency like mean, median. Then we would have seen the in terms of for dispersion, we have seen the variance and standard deviation, and we have seen the coefficient of skewness, and the last is the kurtosis, which describes about the peakedness of the data. And in week 12, the topic is related to the estimation of the risk and reliability for the design of hydraulic structures. So we'll be seeing how to find out the risk and the reliability, and if risk is given, how to estimate the return period, vice versa. These questions are being asked repeatedly in the competitive examination. So we'll be seeing different types of questions, uh, which can possibly come in any of the competitive examinations which you might take. And the risk and the hydrologic risk is used for the design of hydraulic structures like weirs, spillways, and uh, dams. Any hydraulic structure is related to some risk and reliability, so that it performs well under the flooding conditions. So first we'll be seeing how to estimate the measures of central tendency and the rest of the coefficients. So we'll move on to the first question. So a certain hydrological process was found to have a probability density function which is given by f of x is equal to 1 by theta e power minus x by theta, and x varies between 0 to infinity. And this is a kind of exponential distribution. Now we need to calculate what is the mean, variance, standard deviation, coefficient of variation, coefficient of skewness, and coefficient of kurtosis. So we already know what is the mean for exponential distribution. So for exponential distribution, the mean is just nothing but the expected value of x, that is given by 1 by lambda. And if we compare the PDF, the given PDF with this representation, we can find out lambda is 1 by theta. So expected value of x, which is nothing but the mean, is 1 by lambda, which is nothing but theta. So this is the first measure. The next measure is the variance. So we need to find out the variance. So for variance, we know the formula, which is given by expected value of x square minus expected value of x the whole square. Now we already know the expected value of x. Now we need to see how to determine the expected value of x square. So to do that, expected value of x square is equal to integral of 0 to infinity x square f of x dx. So if we evaluate this integral, we'll get e of x square. So we can substitute the PDF in this particular equation. So here the limit varies from 0 to infinity. So x square into, here it is x by theta into e power minus x by theta dx. This is so now we need to evaluate this integral. So we'll be using the integration by parts method. So we'll be taking u as x square by theta, and rest of the terms will be dv, which is e power minus x by theta into dx. Now we need to find out what is du. Du is 2x dx divided by theta. We are just differentiating it. And then for v, we need to integrate the dv. So this will be minus theta e power minus x by theta. Now integral by parts is integral of u dv is equal to uv minus integral of v into dv. This is the formula for integration by parts. Now we'll be substituting the values which we got. So this will be equal to u is x square by theta, and v is minus theta e power minus x by theta, and we need to evaluate this integral over the limit of 0 to infinity minus integral again 0 to infinity minus theta e power minus x by theta, and du we have found as 2x dx by theta. So if we substitute the limit, both the terms will become 0. For the first time when we substitute minus infinity, e to the power of minus infinity is 0. And if we substitute 0, we have x square in the product. So the entire first term will vanish. And here we will have the second term. So again we can evaluate this the second integral by integration by parts. So I am taking u as 2x, and du will be 2 dx, and we have dv as e power minus x by theta, and v will be minus theta e power minus x by theta. So again we can substitute this here. Again this is evaluated over the limit of 0 to infinity. So again the first term will become 0, and the second term will be, here 2 theta is constant, so we are taking it outside, and e power minus x by theta and if we integrate that, we'll get one more minus theta term, and we need to evaluate it over the limit of 0 to infinity. So if we substitute the limits, we will get the answer as 2 theta square. So now we got the E of x square. Now we can calculate variance of x is equal to E of x square minus E of x the whole square. So variance of x is equal to 2 theta square minus, this will be theta square. So variance of x is theta square. So next measure is the standard deviation, which is nothing but square root of variance of x. So this will be theta. The fourth measure is the coefficient of variation. And it is represented by CV. So CV is the ratio of the standard deviation to your mean. So this will be theta by theta, which is nothing but 1. So the coefficient of variation for the exponential distribution is 1. So next measure is the coefficient of skewness. So the coefficient of skewness is given by the equation E of x minus mu the whole cube divided by sigma q. Now we have the standard deviation, but we don't know what is E of x minus mu the whole cube. So we need to find out what is E of x minus mu the whole cube. So for that we need to do some simplification. So what we will do is we will take x minus mu the whole cube. So this is a minus b the whole cube. So we'll be expanding this, x cube minus 3x square mu plus 3 into x mu square minus mu cube. Now we'll be applying the expectation of x minus mu the whole cube. So we'll be applying expectation for each and every term in this equation. So it will become E of x cube minus expectation of a constant is a constant. Then this will be E of x square, and expectation of mean is again the mean, plus three into expectation of x into mu minus mu cube. So now if we can further simplify this. So this will be E of x cube minus 3 into E of x square. We can write the mean as E of x plus 3 into e of x the whole square minus e of x the whole cube. Now we know what is e of x square and what is e of x. Now we need to find out what is e of x cube. So we can find out e of x cube similar to how we found out the e of x square. So e of x cube will be nothing but integration of minus infinity to infinity. Instead of x square, we'll put x cube into f of x dx. So this is the third moment. So if we substitute, this will be integral 0 to infinity x cube into 1 by theta e power minus x by theta dx. So here we can choose u as x cube by theta and dv as e power minus x by theta. So differentiating u with respect to x, we will get 3x square by theta. On the left hand side, we'll have divided by dx, that will come on to the right hand side. So we have dx here. And v is equal to minus theta e power minus x by theta. Now again integration by parts, uv minus integral v du. So 3x square by, so this will be x cube by theta into minus theta e power minus x by theta. We are evaluating over the limit 0 to infinity. Minus integration of v du. So the entire first term will become 0 and theta theta we can cancel. So the rest of the term will be 0 plus 3x square e power minus x by theta dx. So evaluated over the integral 0 to infinity. So we can apply the integration by parts again. I am taking u is equal to x square and dv is equal to e power minus x by theta. So du will be 2x dx and the v is equal to minus theta e power minus x by theta. So again, once again we can apply. So here we have a constant of 3. I have not taken it along with you. So I am keeping it outside separately. So that will be x square into e power minus x by theta, and this is evaluated over the limit of 0 to infinity minus integral v dv. So this will be equal to 6 theta integral 0 to infinity x into e power minus x by theta dx. So again for the last part we can apply the integral by parts. So that will be u is taken as x and this will be e power minus x by theta uv minus integral of v du will be dx. And this we need to evaluate over the limits 0 to infinity. So that will be 6 theta. The first term will become 0 and rest will be if we integrate the second term, we will have theta square and there will be a minus sign x by theta over the limit 0 to infinity. So if we simplify this, we will get 6 theta cube. So we got e of x cube. Now we can find out what is e of x minus mu the whole cube. That is e of x cube minus 3 times of e of x square so e of x square we found it as 2 theta square into e of x plus two times of e of x the whole cube. So that will be 2 theta cube. Here it is mu square Okay, that was a small calculation mistake. So here it is 3e of x into mu square. So that will be 3 mu cube minus we have another mu cube. So we can subtract it and then we can write it as 2 mu cube, which is nothing but 2 times e of x the whole cube. So that is why we are having 2 theta cube in the last term. Now if we simplify this, we will get e of x minus mu the whole cube is equal to 2 theta cube. Once we get this, we can find out the coefficient of skewness divided by sigma cube. Standard deviation is theta, so that cube. So coefficient of skewness for exponential distribution is 2. And the last one is the coefficient of kurtosis. So the coefficient of kurtosis is denoted by the symbol K, and it can be written as x minus mu the whole power 4 divided by sigma power 4. Now we need to estimate what is x minus mu the whole power 4. So similar to e of x minus mu the whole cube, we will expand x minus mu the whole power 4. So for that we need to know what is a minus b the whole power 4. A minus b the whole power 4 is given by a power 4 minus 4a cube b plus 6a square b square minus 4ab cube plus b to the power of 4. So we are just going to apply for x minus b the whole power 4. And if we apply the expectation of x, so this will be e of x power 4 minus 4e of x cube into e plus 6e of x square into mu square minus 4e of x into mu cube plus mu to the power of 4. And we can simplify this similar to the previous one. That will be e of x power 4 minus 4e of x cube into e of x plus 6 e of x square into e of x the whole square minus 3 into e of x the whole power 4. So this will be minus 4 mu to the power 4, and this will be plus mu to the power 4, and that will give you minus 3 mu cube, which can be written as minus 3 mu to the power 4, which can be written as minus 3 e of x the whole power 4. Now in this equation, the only unknown is E of x power 4. Now we will see, we can find out E of x power 4. So similar to the previous x cube, we can integrate and then we can derive this. So if we integrate it and simplify, we will get 24 theta power 4 as the answer. Now we can find out what is x minus mu the whole power 4. That will be 24 theta power 4 minus 4 into 6 theta cube into theta. So all other values we have found. This is e of x cube into e of x plus 6 into e of x square into e of x the whole square minus 3 times e of x the whole power 4. If we simplify, we will get 9 theta power 4. So coefficient of kurtosis is defined by e of x minus mu the whole power 4 divided by sigma power 4, 9 theta power 4 divided by theta power 4. So k will be equal to 9. So this is how you will estimate the different measures like so this brings to the end of the last week's module. So in this, if we see, there is a general trend in the calculation e of x power, that is e of x power e of x square x cube x power 4, so which can be represented as a general trend. E of x power k for the exponential distribution so e of x power k can be written as integral 0 to infinity x power k e of minus x by theta dx, and this can be simplified as theta power k into gamma function of k plus 1. So gamma denotes the gamma function. So if gamma of a number, it is an integer, then we can make use of this formula. So gamma of k plus 1 can be generally written as k factorial. So if it is not an integer, then we need to refer to the tables, gamma function table. So as a complete simplification, we can write e of x power k is equal to theta power k into k factorial if k is integer. So this is the trend for exponential distribution. This is not applicable for any other distributions. Okay, now we'll move on to the second part, which is the estimation of return periods and the risk reliability for a given hydraulic structure. So now we'll move on to the question related to the empirical plotting formulas, which is Weibel's formula, Hazen formula, and that's one more called as California's formula. So the question is recorded 24-hour annual maximum rainfall magnitude for station X is given in the table. So for 10 years, they have given the annual maximum rainfall, that is in centimeters. Now we need to determine what is the return period for the rainfall of magnitude 6 centimeter. First by using the Hazen's formula, and then we need to use the Weibel's formula. So the first step is we need to arrange the given rainfall in the descending order. Arrange the events in descending order. Then we need to assign ranks for the events starting from 1 to m, and we need to find the total number of events, which is represented by capital N. After that, we can make use of the Weibull's formula and the Hazen's formula to find out the probability. Weibull's formula, we have the probability is equal to m divided by n plus 1, which is also equal to 1 by t, which is the inverse of the return period. And we have the Hazen's formula. P is equal to m minus 0.5 divided by n, which is equal to 1 by t. Now in this question you can, if you see the table, you can find out same magnitude of events which have occurred in different years. So when such kind of data set is given to you, the ranking differs little bit. So I'll be showing that here. So this is rainfall sorted, that is arranged in descending order. Then the corresponding rank, then probability using Hazen, okay, we'll be only up to the ranks now. So I'm going to arrange it in descending order first. So 14.2, 13.6, 12 happened twice, then 7.9, again 6 centimeters happened twice, then 4.8, 3.7, 2.9, and we can find out what is the total number of events, that is 10. Next step is to assign the rank. So this will be 1, 2. Since these both events have the same rank, we are going to skip the number 3 and assign rank 4 for both the data. So the calculation is like how many number of times it is equaled or exceeded. So greater than 12, we have 2 events, that is already more, and equaled is twice. So this is exceeded. Events exceeded, that is 14.2 and 13.6. And another one is events equal, so which is nothing but 12, 12. So 12 occurred twice, and 2 events are already exceeding the magnitude of 12. So 2 plus 2 is 4. That is what we basically assign the rank. And next we can continue 5. Again 6. For 6 it is number of events exceeded is 5, and it is equaled twice, so the rank will be 7. So the rank is 7. So the number of events exceeded 5, I am marking with this pink color. So this is 1, 2, 3, 4 and 5, and 2 times it is equaled. So we are writing 5 plus 2 as 7. So again after that we can continue with the running numbers 8, 9 and 10. So we got the rank for different events. Now next step is to determine what is the return period for magnitude of 6 centimeter. So first one is using Weibel's formula. So probability is given by m by n plus 1, which is equal to 1 by t. But we want return period, so that will be P inverse, which is nothing but n plus 1 divided by m. So return period is equal to 11 divided by rank of magnitude 6 is 7. So 11 by 7, that is approximately equal to 2 years. So here you should always round off to the higher value. It will be around 1.56, so I am rounding it off to 2 years. And similarly, by using the Hazen's formula, so we have probability is m minus 0.5 divided by n, which is equal to 1 by t. T is equal to P inverse n divided by m minus 0.5. So T will be 10 divided by rank is 7. 7 minus 0.5 is 6.5, and we can write it as 13 by 2. So that will be 20 by 13. Again, this is approximately equal to 2 years. So only thing you need to be careful is how you are assigning the rank. Okay, we'll move on to next question, which is related to risk and reliability. So the question is, a bridge has an expected life of 15 years and it is designed for a flood magnitude of return period of 100 years. So what is the associated risk? Risk is nothing but that during the lifetime of, during the lifespan of the particular structure, your there is going to be a flood of magnitude of 100 years that's going to happen, and your hydraulic structure is not going to perform as expected. So that is what risk means. So it is the probability of exceedance. So probability of exceedance is written as probability of x greater than xt which can be written as 1 minus probability of non-occurrence, which is probability of x less than or equal to xt. So if we take p as the probability that it is going to happen, then q will be 1 minus p. So p is nothing but 1 by t. This is 1 minus 1 by t. So your risk can be written as 1 minus p to the power of n, which is nothing but 1 minus q to the power of n. Or you can remember it in simple terms. In terms of return period, you can remember, that will be easier. 1 minus 1 by t to the power of n. So t is the return period and n is the design life of the structure. So in this question they have given return period of 100 years and the lifespan as 50 years. So the risk will be 0.395, which is 39.5%. So there is a 39.5% risk that 1 in 100 event, 1 in 100 year event can occur within the 50 years life of the structure. That is what this means. So we can move on to the next question. This question is a little bit tricky question. So a 1 hour rainfall of 40 centimeter has a return period of 25 years. The 1 hour rainfall 40 centimeter or above will occur in each of the 2 successive years. Till now we have seen will occur in 2 successive years or something like that. So we'll be using this kind of the previous question approach to solve the problem, but here they have given each of the 2 successive years. So for every once in 2 years it's going to exceed. So in this case it is a binomial process. So here we can write p as 1 by 25, which is 1 by t, and q will be 1 minus p, that is 24 by 25. Now we need to use the basic equation NCR P power R Q power n minus R. So P is equal to, it is going to occur twice in 2 successive years. So P power R is 1 by 25. It's going to occur twice, and Q power n minus R. So that is 24 by 25 power 2 minus 2. So this will be equal to 0.0016. So here we need to be careful about the word each of the 2 successive years. So the next question is related to the estimation of return period. So in this question, what return period should be adopted in the design of the bridge if you are allowed to have only 5% risk in the 25 years of the expected life of the bridge. So we already know the formula for risk. Risk is equal to 1 minus 1 by t to the power of n. So risk is given as 5%, which is 0.05. 1 by t to the power of 25 is the design life of the structure. So from this we can estimate the value of 1 by t, that is the probability, which will be 1 minus 0.95 to the power of 1 by 25. So once we estimate the probability, we can just take the inverse of it and we will get the return period, which is in this case 487.89 years. Suppose if you are asked to round off this, you need to round off it to a higher value. You should not round off it to the lower value. So we'll move on to the next question. So in this question, a bridge has an expected life of 20 years and the risk that can be taken for the hydrological design of the flood that can be passed safely is 10%. Now we need to find what is the recurrence interval if the risk is 10%. Now we also need to estimate what is the reliability and the risk in this design if this return period is used and the lifespan of the structure is considered as 50 years. So first, the lifespan of the structure is only 20 years. Suppose if the lifespan of the structure is 50 years, what is going to be the risk and the reliability of this particular structure for the same recurrence interval? So the first part is similar to the previous question which we solved. So that is risk is equal to 1 minus 1 by t to the power of n. So risk is 10%, that is 0.1 minus 1 minus 1 by t to the power of for the first part lifespan is 20. So from this we can estimate the return period as 190.3 years. So we need to use a return period of 191 years in our design, or maybe 200 years also we can take. Now in the part B of the question, the return period is the same, which is 190.3 years, but the lifespan has increased to 50 years. Now we need to find what is the risk and the reliability. So we can find out the reliability, which is 1 minus 1 by t to the power of n. So reliability is equal to 1 minus 1 by 50, 1 minus 1 by 190.3 to the power of 50. Reliability is equal to 0.768. So that is 76.8%. Then we can find out the risk as 1 minus reliability, which is 23.2%. So which is 0.23. So there should always be a trade-off between risk and reliability. We cannot design a structure which is 100% reliable. It will lead to unreasonable capital cost for construction and maintenance. So we will always design it for a optimum level such that the cost is minimum and there is a good reliability also. Okay, we'll move on to the last question for the day. This question is I'll be introducing to a new term. So the mean and the standard deviation of the annual flood series at a bridge site is 5651 meter cube per second, and standard deviation is given as 1066 meter cube per second. The bridge structure is to have a lifespan of 40 years. However, if it is designed for a return period of 80 years, then we need to determine what is the risk that is involved, which is similar to the previous question. If the actual flood discharge used in the design is 10,000 cubics, then we need to determine whether there is a safety margin for the design or not. So this is the new term, safety margin, for the design. And we can assume that the design flood holds good for Gumbel distribution. And the last part of the question is, if the risk is limited to 20%, then what should be the return period, which is similar to the previous questions which we saw. So part A of the question. So N is 40 years, which is the lifespan of the structure, and the return period is given as 80 years. So we need to find out what is the risk. So that is 1 minus 1 by 80 to the power of 40. So the risk associated with it is 39.5%. So next we can move on to the part B of the question. So the design flood is corresponding to a return period of 80 years and follows, we can assume that it follows Gumbel distribution. And the mean is given as 5651 meter cube per second, and the standard deviation is given as 1066 meter cube per second. So if it follows Gumbel's distribution, we need to determine what is the corresponding xt value for the return period of 80 years. So for that we need to find out the Gumbel's parameters alpha and beta. So we know that mean can be written as beta plus 0.5772 alpha, and variance, which is sigma square, can be written as pi square alpha square divided by 6. So from this we can estimate the alpha as square root of 6 sigma divided by pi. And if we have alpha, we can estimate beta as x minus 0.5772 alpha. So first we can find out what is beta. That is square root of 6 into 1066 divided by 5651, that is 831.16, and beta can be estimated as, mean is given as 5651 it's divided by pi. 5651 minus 0.5772 into 831.16, which is alpha. So we can find out beta as 5171.256. So now we have the parameters alpha and beta. Now we need to find out what is the value of x. So if you remember, we have written the transformation for the Gumbel's distribution. Yt is equal to x minus beta divided by alpha. So here x is xt, which is the value of the design flood, but we need to estimate what is yt. So yt can be written as minus ln of ln t divided by t minus 1. This was derived in the lecture videos. So yat is equal to minus ln of ln 80 divided by 79, which will give yat is equal to 4.375. Now once we have yt, we can find out what is x. So 4.375 is equal to xt minus beta, that is 5171.256 divided by alpha is 831.16. So if we calculate, here xt is nothing but x80, that's what we are finding out. So if I calculate, it is 8807.58 meter cube per second. So if the structure is designed for, in the part B, the structure is designed for 10,000 cumex, and for a corresponding return period of 80 years, we have the discharge as 8,807.58. Now, safety margin. Q design minus Q for a particular return period that is provided. So this will be 10,000 minus 0.58. Safety margin is equal to 1192.42 meter cube per second. You can also find out in terms of percentage, or if you want to find out in terms of a percentage, then percentage safety margin Q design minus QT divided by Q design. So you can find out in terms of percentage also. And part C of the question, if the risk is limited to be 20%, then what should be the return period? So if the risk is 20%, then we can find out what is the return period. So from this, if we estimate, the value of the return period will be 179.75 weeks. So I hope this session is useful. In the next session, we'll be seeing how to design a storm drainage network by using the rational method for a small urban catchment. Thank you.